Hi everyone, my name is Lydia, and this is what I wish they taught me about econometrics and introduction. Robust standard errors fix our inference under heteroscedasticity, but they don't change the estimation itself. So now we ask a more ambitious question. Can we actually improve our estimates when variance is non-constant? In fact, that's what the weighted least squares does. The problem with OLS is that the OLS minimizes the sum of squared residuals. So we have seen countless times, this is the minimization of the sum of the residuals square I from 1 to n. And in here, every observation gets the same weight. A noisy observation counts just as much as a precise one. And under heteroscedasticity, that's inefficient. We're treating unreliable data the same as reliable data. OLS is still unbiased under heteroscedasticity, but it's no longer the most efficient unbiased estimator. So the Gauss-Markov theorem requires homoscedasticity. And when that fails, it means like we no longer have that fourth statistical property that we really liked, meaning OLS is no longer our blue estimator with the lowest variance. So what if instead we gave more weight to precise observations? And less weight to the noisy ones. Well, that's what the weighted least square does. So the weighted least squares, so if OLS did this, the weighted least squares now is actually going to minimize the sum of WI being the weight for every observation times U square I for I going from 1 to n. So now we've got a weight specific to each observation, okay? So same objective, as the OLS. However, instead of minimizing the squared residual by giving every observation the same weight, now every observation has its own weight. Think of it like taking an average of now only expert or mainly expert opinions instead of you mixing up expert opinions with just a random guesser. If one expert is very reliable and the other, let's say, it's highly unpredictable, you'd weight the reliable expert more heavily. So weighted least squares does the same for observations. Tightly clustered observations, reliable, more weight. Widely spread observations, there's noise, they get less weight. And this is why the weighted least square produces more efficient estimates when the weights are correct. Okay, so it's another way of using the data, but more intelligently. So how are weights chosen would be the most common follow-up question. The ideal weight for each observation, weight for each observation would be 1 over the variance of UI. Okay, so in a sense, it's 1 over the sigma square I, because in this case, the sigma square will be different for every observation. And because it's 1 over the sigma square I here, you can see a higher variance will mean a smaller weight, which means observation matters less. And a lower variance would mean that there is a larger weight and the observation matters more. If we use true variances, the weighted least square gives us the best linear unbiased estimator because it restores the Gauss-Markov theorem, basically. And this is a very key theoretical result because weighted least squares with true weight is blue. OLS under heteroscedasticity, it's not. The weighted least squares is what OLS would be if basically all observations were equally reliable. What improves with the weighted least squares compared to normal OLS? So compared to OLS, which we know that now under heteroscedasticity, we can no longer trust any of the t-test p-values or confidence intervals, the weighted least squares gives us more efficient estimates. Okay. It gives us correct inference. So no need for robust standard errors if the weights are right. And it will give us, as we said, the blue estimator. So the best possible linear unbiased estimator. Keep in mind, the weighted least squares doesn't just fix the standard errors, it improves the estimates themselves. However, there is obviously critical limitations because the problem is we almost never know the true sigma square I in here. So in practice, we have to estimate the weights, which introduces its own uncertainty. And again, if the weights are right, we know that the weighted least squares will give us the blue estimates. But if the weights are wrong, then in that case, the weighted least square can perform worse than what OLS would have performed under heteroscedasticity. So a badly specified weighted least square is worse than a correctly specified OLS with robust standard errors. This is also one of the practical reasons why robust standard errors dominate in applied work. They require no knowledge of the variance structure, just the residuals. The weighted least squares requires you to model the variance, which is basically adding more assumptions that can potentially fail. Ultimately, if we were to compare with robust standard errors, the robust standard errors would fix inference and it would require nothing else but the residuals. The weighted least squares would fix estimation and efficiency. However, it would require knowledge of variance structure, which sometimes would make weighted least squares maybe a less ideal option than the robust standard errors. Okay. This completes also the heteroscedasticity arc. Keep in mind, in most of the stuff that you could be asked in exams regarding this topic is mostly identifying whether you have heteroscedasticity or not, and then simply stipulate what are the solutions to it, which most of the times is using robust standard errors. And in practical work, most of the times what will happen is that you'll always be asked to add robust standard errors to whichever estimation, regardless of whether you know there is heteroscedasticity or not. We've covered now what it is, what it matters, how to detect it, and ways to address it. The next problem that we're going to move on are endogeneity and the solution to it, instrumental variables. So stay tuned, and I'll see you in the next video.